All right, let's see if I can properly reproduce what I was trying to do in class in section 3.1.6. So this is the second uniqueness theorem. We have a blobby blob blob. Why not try and draw it? There's a bunch of little conductors in here. They have a total charge. We don't know how that charge is distributed. And then we have a volume out here, and there is some kind of charge distribution defined by rho in there. So we've got our volume with a bunch of conductors and charge in it. So we want to show that there is, if we know what the charge density is and what these total charges are, then we will only get one solution for the electric field. So the proof, as with the first one that we did in class, is to assume two fields satisfy the problem and see what happens. So break the uniqueness theorem first. So we have E1 and E2, 1 over epsilon, not rho. They're based on two different fields based on the same rho, the same charge density, and that works in space between conductors. Okay? All right. We also want to define these electric fields on the surface of each conductor. And that has to follow Gauss's law. Gauss's law in the differential form here, and that for the space in between, and Gauss's law in the integral form here. And he counts these as I, right? So this is A, B, C, D, right? I1, I2, I3, I4. It's just counting through each of them. But for any one of those surfaces, the electric field dotted with the area, right, of that surface is equal to 1 over epsilon naught, the Q that's inside that particular surface. And that has to equal the same. Oops, that's an I. Okay, so it's saying these two electric fields are both valid solutions. Two both valid solutions for the same, each one of those conductors, their surfaces, right? So these are both working. These are both solutions that can come from those surfaces. Okay, so this is on conductor surfaces. And I think the reason we have so much going on is he's trying to show us the proof of the theorem. There is a hair across the field of view, and it's driving me crazy. I swear it's not real. It's from one of my Dragon Con wigs. I think we're just gonna have to live with it. Sorry. Oh no, it's the wire. Okay, I'm not editing this video. So this is throwing in all the scenarios you could possibly have in one situation, right? You have conductors and you have blobs of charge. And then the outer boundary also needs to satisfy, right? Outer boundary, that's the outer boundary of this volume, also needs to satisfy Gauss's law, right? The flux of the electric field coming out through that outer boundary is determined only by the total charges inside. And that has to work for both of our electric fields that we are claiming are both valid solutions. Q tote. All right. So now we're going to look at a third electric field, which is what happens if you subtract one from the other. All right, so this third electric field exists, let's say. So if we take the effects of electric field 2, say just in the space between conductors, in space between conductors, Electric field 2 is determined by rho. If we subtract out electric field 1, which is also determined by rho, we find that divergence is 0. Right? Because, you know what, well, I want to do that because the whole point of me doing this because he doesn't do it enough in the book. So if we had the divergence, right, of E2 minus E1, which is the divergence of E2 minus the divergence of E1, right? Well, those were equal to each other up here. So rho over epsilon naught minus rho over epsilon naught equals 0. Okay. So that is a fundamental property of the difference between the two fields. That is going to come useful real soon. And that's in the space between conductors. Cool. All right. Over each boundary surface. Over each boundary. And this could be the overall boundary of this volume, or it could be the individual conductor boundaries. Doesn't matter. If we take E3 over that boundary, dA, whoops, equals 0. Oh, wait, actually, no, I'm going to show it equals 0. So that's E2 minus E1 dot dA equals, these end up separating, minus E1 dot dA, which we saw depends on, right, the charge enclosed. And the same charge enclosed, so that also equals 0. So let me rewrite the solution to that. All right. So this third field, which is the difference between the two fields that we are claiming are solutions, has these two properties. Okay, let me take this out so we don't know. So we don't know. I'm going to leave this over here. So we don't know how the charges are distributed, but we do know for a conductor, the surface is an equipotential. So, right, so V3 is constant, and this is constant, right? And this is the potential of this electric field, that is the difference of the two electric fields. Okay. So, this is the part where I always get lost. Oh, right. Yeah, so we're going to take this property, and in for E3, we're going to put this potential. I'm going to pull the negative out just because I can. Right? And we want to see what that turns out to be. So this is the one that is product rule number 5, which I, right? La 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 la. I'm going to go find that one. Oh, I know where it is. No, I don't know where it is. Product rule number 5 is in the exam folder. Crap, no, it's not. Ugh. Course docs. There it is. Equation pages. Okay. Product rule number 5 says that this is a function and a vector field. Is the function dotted with A plus, we ran out of room, plus A dotted with the gradient. Okay, I'm going to pause here and collect my thoughts. Okay, I was jumping ahead trying to stick V in for that. That's not what we want. Okay. So we're taking this product rule, and F here is a scalar field or function. This is a vector field. And we're going to put in V for the scalar field and E for the vector field. And basically see what happens. So that is the scalar field. I feel like I'm jumping off a cliff here. Right, plus E3 dotted with the vector field. Okay. Okay. So, now we use the fact that E3 is equal to gradient of the potential. And we are going to insert it here. That's where that comes from. So that means that's V3. Oh, right. And we're going to use one other piece. Back here, we saw that the divergence of this electric field is 0. So this term equals 0. We're going to plug in E3 there. So we're going to get, so that's 0 plus E3 dotted with itself. Whoops, and there's a negative sign there. Negative sign. We get negative E3 squared. So when you, take the dot product vector times itself, you get its magnitude squared. Sorry, that's ugly. Okay. Phew. Now. We're going to integrate this bad boy over that volume. So in applying the divergence theorem, so we have integrating over a volume. This is what we started with. This is one of those, who thought of this? I don't know. Probably took a whole lot of trial and error, because why would you think to put those together? But it works. All right, so the divergence theorem tells us, that this volume integral of this divergence is the same as the closed surface integral. Words are hard. dA, that. So the volume, volume integral of the divergence is equal to just the surface integral, closed surface integral of whatever that vector field was, or whatever that mess is, dotted with the area. We've already gone through and shown that that is equal to negative E3 squared. And the dog is trying to get my attention. Poor thing. Oh no. Okay, the dog's having trouble. I'll be back. Okay. Got to think about that while I took the dogs outside. Why are we doing this? Sometimes I look through these proofs and I'm like, why are we doing this? We are investigating the properties of E3, which is the difference between the two potential solutions. Potential is the wrong word. The two possible solutions for this scenario. So if we can figure out properties of this, spoiler alert, we're going to see that this field is 0, right? So that these are the same. That's kind of what the first proof did as well. The reason for doing it this way is because it works. Someone figured out that this is the way to prove it. I can't even begin to imagine the trial and error that it took to get to this point. But anyway, point is, because of the product rule, we can replace this with negative E3 squared d tau. Okay, so let's rewrite the relevant parts of this, which is the surface integral dot dA equals negative volume integral E3 squared d tau. Okay. This looks at all of the boundaries in the regions in question. Great. Okay, but we've already stated that the surface surface boundaries are equipotentials, meaning that's a constant. So that can come out. And we have a surface integral of E3 dot dA equals negative V E3 squared d tau. Okay? Oh, this part connects to this property we already found of E3, right? That the flux through a closed surface is 0. Well, okay, that tells us that, well, screw the negative, we don't care anymore. V E cubed squared d tau equals 0. So this is the final property of E3 that tells us where we want it to go. So the only way you can integrate over a volume and get 0, right? That field would, whatever you're doing the integral of, would have to have positive and negative components that canceled out. But this is the field squared. So this is always, right, positive. Can't be negative. So in order for it to be 0, E3 itself must be 0. Or I guess you can say, you know, magnitude is 0, which gives you the same thing. So this whole long-ass proof is to set up these two possible solutions, E1 and E2, right? Show their properties. Use those properties to define E3, which is the subtraction between the two, right? And define its characteristics. And its characteristics are that its divergence is 0, the integral over the surface, closed surface, is 0, and then using nice little trickery is not a great word, but hey, it works. Using a product rule, showing also that when you integrate its magnitude squared over any volume, you also get 0. And so it's 0. It has to be 0. Weird. It's slightly long and convoluted, but I hope this showed you a little bit more of the extra steps that are happening in between when you look at that in the textbook.